Okay, the next type of differential equations we're going to be looking at are called exact equations, and they're of the following form. The partial of a function f with respect to x dx plus the partial of a function f with respect to y dy equals 0. Another alternative form is m of a function xy dx plus n of a function xy dy equals 0. So just by comparing these two expressions, we can clearly see that df dx is equivalent to mxy. Now, mxy and nxy are basically functions involving functions of x and y. So, in other words, df, the partial of f rather, with respect to x equals m, and the partial of f with respect to y equals n. Now, to solve a differential equation that's an exact equation, we need to first show that the differential equation is in fact exact, and we do that by taking the partial of m but with respect to y, and we need to show that it equals the partial of n but with respect to x. Once we have shown this, once this condition is satisfied, the differential equation is now exact and we can proceed and solve for it. Once we have done that, we establish a function f, a general form of that function. We'll take the partial of the other variable. So depending on how you start the problem, you can either start with the expression for m or n. If you're going to start with m, you're going to find the partial with respect to y, and n, you can find the partial with respect to x. But this is all, it's not very clear at the moment because we haven't done an example yet. So let's just get into an example and go through it step by step. So, okay, so the expression 5x plus 4y dx plus 4x minus 8y cubed dy equals 0 is of this form over here. So 5x plus 4y is m, and 4x minus 8y cubed is n. So what we need to do now is to show that this differential equation is exact. So we're going to take the partial of m with respect to y and the partial of n but with respect to x, and show that these two expressions are equal. So m is 5x plus 4y. We're going to take the partial of m but with respect to y. So the term 5x, because it doesn't contain any y's, we don't consider that at all because we're taking a partial derivative with respect to y. The derivative of 5x with respect to y is just going to be 0 because the derivative of a constant is 0. So this doesn't form any part of the differential. dm dy, the partial of m with respect to y, so the derivative of 4y is just going to be 4. And then likewise for n, which is 4x minus 8y cubed, we're taking the partial of n, but with respect to x. So any term that doesn't contain an x is treated as a constant. So minus 8y cubed, when you differentiate with respect to x, that's just going to be 0. So that takes no part. The derivative of 4x with respect to x is just going to be 4. So clearly we can see that the partial of m with respect to y equals the partial of n with respect to x, which is 4. So therefore, the differential equation is exact. Okay, now that we've shown that this differential equation is exact, what we're going to do now is write down the expression for m, which is 5x plus 4y, and we know that m is the partial of f with respect to x, and n is 4x minus 8y cubed, and n is the partial of f with respect to y. So what we're going to do now is we're going to take this expression, m equals 5x plus 4y. We can also start with n. We'll do both cases. So we take either m or n, find the partial with respect to the other variable. So if we start off with m, which is the partial of f with respect to x, we're going to take this expression And so we're going to take df dx, which is 5x plus 4y. What we want to do now is find the function f, right? A general form of the function f. That's what we're trying to find, is the function that gives us this differential equation here. So to take a partial derivative and look for a function, we're going to have to integrate both sides, right? So if we're going to choose, and we don't have to do both, right? You can choose to either work with the expression for m, which is the partial of f with respect to x, or you can do similarly for n. You don't have to do both. We are going to do both just so that it's clear how to solve exact equations. So we're going to take, we'll start with m. We'll take the expression m, which is the partial of f with respect to x, and we're going to integrate that with respect to x, right? Because the partial here is with respect to x. Alternatively, the partial of f with respect to y is 4x minus 8y cubed. To find the function f, we're going to integrate that now, but with respect to y. So we're going to integrate 4x minus 8y cubed with respect to y. Just to reiterate, you don't have to do both. You either work with m or n. So let's just start with m. So integrating the partial of f with respect to x is just going to give us the function fxy, and that equals, we'll just write this out again, the integral. We're just going to split this up because that's a property of integrals. We can express this single integral as the sum of two integrals. So it'll be the integral of 5x dx plus the integral of 4y dx. I'm just going to come up here. 5 is a constant. So we're going to take the 5 out of the integral sign. We have the integral of x dx. And with respect to x, 4y is a constant. So that whole term 4y will be written outside the integral sign because you're integrating with respect to x, and it'll be the integral of 1 dx. So fxy equals 5 times the integral of x with respect to x is going to be a half x squared plus 4y times the integral of 1 dx with respect to x is just going to be x. Now, normally we add c for the constant of integration, but because we are dealing with a function of x and y, this constant we're going to refer to as another function, but it's a function only of y, so such as g of y. When we differentiate this expression here for f with respect to x, though, right? We're coming back to this. We integrated with respect to x. So when we take the derivative with respect to x, or this expression here, the derivative of a function that contains only the variable y is going to be 0. The derivative of a constant is always going to be 0. So that's why we call this g of y not c, is because we're trying to find a function that contains a function of x and y. So the next step is to now find the partial derivative of this expression for f, but with respect to y. Remember that n is the partial of f with respect to y. So we started with m, which is the partial of f with respect to x, integrated with respect to x, got an expression for the function, and we've now got a constant, g of y, that's included in that expression. We take the partial of this with respect to y, and then we tie it back to the expression for n. So taking the partial of f, but with respect to y, the first term, 5 over 2x squared, with respect to y is a constant term, so that's going to be 0. The partial of 4xy with respect to y is just going to be 4x. And the partial derivative with respect to y of g of y is just going to be g prime y. Now, df dy, which is the expression for n, is 4x minus 8y cubed. So we're now going to compare these two expressions here. So we have 4x and 4x, and g prime y and minus 8y cubed. So clearly we can see by equating these two expressions, we can see that g prime y is minus 8y cubed. Now, because this is our expression for the function f, okay, we have an unknown quantity in g of y here. We want to know what that g of y is. So we're going to take this expression for g prime y and integrate it. So with respect to y, so integrating with respect to y will give us minus 8. Integrating y cubed will give us y to the 3 plus 1, so it's going to be y to the 4. And we divide by that exponent, which is 4. So g of y equals minus 8 times y to the 4 over 4, which is minus 2 y to the 4. And now we have this expression for g of y. So the function f equals 5 over 2 x squared plus 4xy minus 2y to the 4. Now before we approach it from the perspective of n, we just want to check that the solution is correct. Okay, so we're going to take the function that we've just found for f, 5 over 2x squared plus 4xy minus 2y to the 4. And we're just going to take the partial with respect to x. So if we're looking for df dx, we'll start with that, we'll do n as well. So with respect to x, we can have 5 over 2 times 2x plus, with respect to x, 4y is going to be a constant. Okay, the derivative of x is just going to be 1. And the derivative of minus 2y to the 4, there's no x's contained in this term, so the derivative with respect to x is going to be 0. So df dx will be 5x plus 4y, which agrees with this expression for m, which is 5x plus 4y, partial of f with respect to x. We have that here. And now we're going to do the partial of f, but with respect to y. So the first term, 5 over 2x squared, when you take the partial with respect to y, is going to be 0. The second term, the partial derivative of 4xy with respect to y is just going to be, 4x is the constant, so it's just going to be 4x times 1. And then the partial derivative of minus 2y to the 4, but with respect to y, is going to be minus 2 times 4 is 8y cubed. So it's 4x minus 8y cubed, which is the expression for n. So the solution is correct. So this is your expression for f, but the solution to that is actually written as 5 over 2x squared plus 4xy minus 2y to the 4 equals a constant c. So this is how your function is represented. Okay, now we're going to go back and we're going to do the same thing, but we're going to take the partial. We're going to work with n and find the partial of that. So now we're going to start with n, which is the partial of f with respect to y. So the partial of f with respect to y is 4x minus 8y cubed. Whereas previously we started with m and integrated with respect to x, we are now going to take n and integrate with respect to y. So on the left we'll have the function itself, fxy equals, again we're going to split this up into two integrals. So 4x dy minus the integral of 8y cubed dy, just coming back up here. So with respect to y, 4x is a constant, so it's going to be 4x integral of 1 dy minus, we can take the 8 out because that is a constant, the integral of y cubed dy. That'll give us 4x. Integrating 1 with respect to y is just going to give us y. Integrating y cubed with respect to y will give us y to the 4 over 4. And because we're integrating with respect to y, this constant of integration is now going to be an expression involving only x. We'll call this g of x. Just cleaning this up. 4xy minus 2y to the 4 plus g of x, and this is now f. We're going to take the partial now of f, but with respect to x, and then we're going to match it up to m. So m is the partial of f with respect to x. We're going to take the partial of this expression now, but with respect to x. So the derivative of 4xy with respect to x is just going to be 4y. The derivative of x is 1, so we're not going to put that 1 in. The derivative of minus 2y to the 4, but with respect to x, is going to be 0 because there are no x's here. So everything's treated as a constant, and the derivative of a constant is 0. Plus the derivative of g to the x, which is a function containing only x, a function only of x. When you differentiate with respect to x, is just going to be g prime x. And we're now going to compare this expression to what m is. M is 5x plus 4y. So just writing this out again, df dx, the partial of f with respect to x is 4y plus g prime x, and the expression for m, which is the partial of f with respect to x, is 5x. Let's write it this way, 4y plus 5x. So we have the 4y here, and then we have g prime x and 5x. So clearly g prime x equals 5x. So to get the function g of x, we're going to integrate both sides with respect to x. So we will have 5 times the integral of x will be a half x squared, which is, so 5 times half x squared is 5 over 2 x squared. So the function f is 4xy minus 2y to the 4. G of x is 5 over 2x squared, which is exactly the same expression for f that we got previously. Okay, this example is also in the mn form. So 2xy squared minus 3 is m, and 2x squared y plus 4 is n. So remember that m is the partial of f with respect to x, n is the partial of f with respect to y. N is the partial of f with respect to y. So again, we need to first show that the partial of m with respect to y equals the partial of n with respect to x. So m is 2xy squared minus 3. N is 2x squared y plus 4. So the partial of m with respect to y is going to be 2x as a constant, so it'll be 2x times the derivative of y squared will be 2y, and then derivative of minus 3 with respect to y will be 0. Minus 3 is a constant regardless. So the partial of m with respect to y is 4xy. Now the partial of n with respect to x, anything that isn't an x is a constant, so we'll have 2y, and the derivative of x squared will just be 2x. The derivative of 4 constant is going to be 0, so the partial of n with respect to x will be 4xy. So clearly we can see that the partial of m with respect to y equals the partial of n with respect to x. So they both equal 4xy. So therefore we have an exact differential equation. The next thing we need to do is we either take m or n and integrate the expression for that, and then take a partial with respect to the other variable. So we'll do, in this case, we'll do both cases, m and n. So we're starting with m. M is the partial of f with respect to x. That equals 2xy squared minus 3. We're now going to integrate these expressions with respect to x. So we have the function fxy equals integral. Just going to write this out as 2xy squared minus 3 dx. And then just coming up here, we'll have the function f equals, again we're going to split this up into two separate integrals. So the integral of 2xy squared dx minus the integral of 3 dx. 2 is a constant, so we can write it outside the integral sign. The integral of xy squared dx minus, again take the 3 out, the integral of 1 dx. We're now integrating with respect to x, so anything, in fact this y squared could have been taken out as well as a constant, it really does not matter. The integral of x with respect to x will be a half x squared minus 3. The integral of 1 with respect to x will just be x. But instead of writing the constant of integration as c, because we integrated with respect to x, the constant here we're going to call a function g of y, which contains only y. It's a function of y only. Just cleaning this up, f 2 times a half is just going to be 1, so we'll have x squared y squared minus 3x plus g of y. We are now going to take the partial of f, but with respect to y. The reason is we want to match this expression for the partial of f with respect to y back to n, since we have an expression for n which is the partial of f with respect to y, and you want to match those two expressions up to find what this function g of y is, and hence find what the function represents. So the partial of f with respect to y, anything that isn't y is a constant, so we'll have x squared times the derivative of y squared will just be 2y. The derivative with respect to y of minus 3x is going to be 0, because that's considered to be a constant term. And the derivative of g of y with respect to y is just going to be g prime y. And we know that the partial of f with respect to y, which is n, is this expression here, 2x squared y plus 4. So we have two expressions. I'm just cleaning this up. This is 2x squared y plus g prime y. We can clearly see, comparing the two expressions for df dy, 2x squared y appears in both, which is a good thing. If that wasn't the case, you know that you've done something wrong. And then we have g prime y and the other term 4. So clearly we have g prime y equal to 4. So integrating that, g of y will be equal to 4y. So the function that we're looking for is fxy equals x squared y squared minus 3x plus g of y is 4y, and that equals c. And this is your solution. We're going to solve this differential equation, but from n's perspective in a second. Just want to check that this solution is in fact correct, if this is a function of the function that gives us this differential equation. So if we're looking for the partial of f with respect to x, we will have y squared is the constant. So let's just put the constant down first. The derivative of x squared will be 2x. The derivative of minus 3x with respect to x is minus 3. And the derivative of 4y with respect to x is going to be 0. So this equals 2xy squared minus 3. And this expression here, 2xy squared minus 3, is the expression for m. So that is correct. Now, the partial of f, but with respect to y, y is now the variable we differentiate with, so x squared is your constant. The derivative of y squared is 2y. The derivative of minus 3x with respect to y is going to be 0, because this is treated as a constant with respect to y. And the derivative of 4y with respect to y is going to be plus 4. So cleaning that up, we have 2x squared y plus 4. And this expression here for the partial of f with respect to y is the same as that for n. So this solution is correct. We're now going to we're going to solve this differential equation, but from n's perspective. Okay, so n is the partial of f with respect to y, and that equals 2x squared y plus 4. So we're now going to integrate this expression. So it'll give us the function fxy equals, again we're going to express this integral as the sum of two integrals. So 2x squared y, and we are integrating with respect to y here, plus the integral of 4 dy. Choose a constant, and with respect to y, x squared is also constant, so we'll take 2x squared out, and we have the integral of y dy, plus, and 4 is a constant, so we'll take that out, integral of 1 dy. Just coming up here, that'll give us 2x squared times the integral of y with respect to y is a half y squared, plus, and then 4 times the integral of 1 with respect to y is just going to be y. Again, we are not going to put c here for the constant of integration. Because we integrated with respect to y, we can have a function here which we'll call g of x. It's a function of x and x alone. The derivative of that with respect to y would be 0. Okay, so this will mean that the function fxy equals, just clean this up, 2 times a half is 1, x squared y squared plus 4y plus g of x. We're now going to take the partial of f, but with respect to x. The reason is we want to match this up to the expression that we had for m, which is the partial of f with respect to x. So with respect to x, y squared is your constant, so we'll just put that out in front. The derivative of x squared is 2x. The derivative of 4y with respect to x is going to be 0, because 4y is the constant with regard to 0, with regard to x rather. And the derivative of g of x will just be g prime x. Just clean that up, 2xy squared plus g of x. The partial of f with respect to x is m, which is 2xy squared minus 3. So comparing these two expressions for the partial of f with respect to x, we can see that we have 2xy squared in both expressions, and g prime x and minus 3. So clearly g prime x must equal minus 3 for these two expressions to be equal. So integrating, g of x will therefore be minus 3x. So the function f will be x squared y squared plus 4y plus g of x. X squared y squared plus 4y minus 3x. And that's the same expression we got when we started with m. Okay, again, this differential equation is in the mn form, so sine y minus y sine x will be m, and cos x plus x cos y minus y be n. So m, again, is the partial of f with respect to x. N is the partial of f, but with respect to y. So again, we need to show that the partial of m with respect to y equals the partial of n with respect to x. So m equals sine y minus y sine x. So the partial of m with respect to y, the derivative of sine y will be cos y. With respect to y, sine x will be a constant, in fact minus sine x. So we'll just write that down. And the derivative of y will be 1. So 1 times minus sine x will be minus sine x. So this is the expression for the partial of m with respect to y. And then likewise with n, which is cos x plus x cos y minus y. We want the partial of n, but with respect to x. So the partial derivative, the derivative of cos x with respect to x will be minus sine x. We're differentiating with respect to x, so plus cos y is a constant, so we'll just put that out in front. And the derivative of x is 1, 1 times cos y is cos y. And then, the derivative of minus y with respect to x will be 0. So comparing the two, just write this as the positive term first, cos y minus sine x. We get the same expression. So therefore, the partial of m with respect to y equals the partial of n with respect to x. So therefore, the differential equation is exact. So we'll start with m again. The partial of f with respect to x is sine y minus y sine x. We can integrate both sides with respect to x. So on the left we have the function itself, f, xy. We're integrating with respect to x. Again, let's just split this up into two separate integrals. So the integral of sine y dx minus the integral of y sine x dx. Sine y is a constant with regard to x, so with respect to x rather, so sine y, the integral of 1 dx, minus with respect to x, y is a constant, so we take that out, and we have the integral of sine x dx. So we have sine y, the integral of 1 with respect to x will just be x, minus y times the integral of sine x is minus cos x. The derivative of negative cos x is sine x. So the integral of sine x is negative cos x. Instead of the constant of integration being called c, we're going to call it g of y because we integrated with respect to x. So when we differentiate with respect to x, the derivative of a function of y is going to be 0. So just cleaning this up, we have x sine y plus y cos x plus g of y. We're now going to take the partial derivative of f, but with respect to y, and we're going to match it up to the expression we have for n. So the partial of f with respect to y, x is a constant. The derivative of sine y with respect to y is going to be cos y. With respect to y, cos x will be a constant, so it'll be plus cos x, and the derivative of y is going to be 1. 1 times cos x is cos x, and the derivative of g of y with respect to y is going to be g prime y. We're now going to compare this expression to the expression for n, which is cos x plus x cos y minus y. So we have x cos y in both expressions. We have cos x and g prime y and minus y. So clearly g prime y must equal minus y. And integrating that to find the function g of y will give us minus a half y squared. So the function f equals x sine y plus y cos x minus a half y squared. And what we want to do is we want to just check the solution. So if you just put that equal to c, then this would be the solution. But we just want to find the partials of f with respect to x and y and check that we get this differential equation. So the partial of f with respect to x, sin y is a constant. The derivative of x is 1. So 1 times sin y is sin y. We're differentiating with respect to x, so y is a constant. So just put the y down. The derivative of cos x is minus sin x. And with respect to x, minus a half y squared is a constant. So df dx is sin y minus y sin x, which is the expression we have for m. So that checks out. And then the partial of y, of f rather, with respect to y, x is a constant. The derivative of sin y is cos y. With respect to y, cos x is a constant, so we'll just put the cos x there. The derivative of y is 1. 1 times cos x is cos x. And then the derivative of minus a half y squared with respect to y is going to be minus a half times 2y, and that equals x cos y plus cos x minus y. And that is the expression that we have for n. Cos x is just rearranged. We have cos x, x cos y, and minus y. So that also checks out. So the solution is correct. Okay, here we have m being tan x minus sin x sin y, and n being cos x cos y. So again, the first thing we need to do is show that the partial of m with respect to y equals the partial of n with respect to x. So m is tan x minus sin x sin y. So partial of m with respect to y will be the derivative of tan x with respect to y is going to be 0. Tan x is a constant with respect to y. Then we have minus sin x sin y. So we'll start with minus sin x, which is a constant with respect to y. The derivative of sin y is cos y. So that's just going to be minus sin x cos y. And then n is cos x cos y. So the partial of n with respect to x will be, cos y is a constant, so we'll just put that down in front. The derivative of cos x with respect to x is minus sin x. Cleaning that up, it's minus sin x cos y. So these two expressions are equal. Therefore, the DE, the differential equation, is exact. Okay, now since m is the partial of f with respect to x, that equals tan x minus sin x sin y. We're now going to integrate these expressions with respect to x. So the function fxy equals, again, we're going to split this up into two separate integrals. So we have the integral of tan x dx minus the integral of sin x sin y dx. The integral of tan x with respect to x is ln sec x. With respect to x, sin y is a constant, so we'll just take that outside the integral sign. And then the integral of sin x with respect to x is minus cos x. Again, we are integrating with respect to x, so the constant of integration will be a function of y. So we'll just have g of y to represent that constant. We're now going to take the partial derivative of f with respect to y, and we're going to equate the resulting expression to the expression we have for n, which is also an expression for the partial of f with respect to y. So with respect to y, ln sec x is a constant, so the derivative of that will be 0. With respect to y, cos x is a constant, so we'll just put that out in front. The derivative of sin y is cos y, and then g of y being a function of y, the derivative of that will be just g prime y. So comparing these two expressions now. N is cos x cos y. So we can clearly see we have cos x cos y in the first expression and in the expression for n. And then g prime of y, we're going to equate to 0. So g prime of y equals 0. When we integrate that, we're just going to get a constant term. We'll just call that c. So the function f is given by ln sec x plus cos x sine y plus c, and that will equal c sub 1 if you like, or any other constant. C and c sub 1 are just arbitrary constants. You can just clean this up a little bit. Since we have two constants here, you don't really want to have two constants as part of your solution. So ln sec x plus cos x sine y, and these two constants together, whether you add or subtract them, is irrelevant. We're just going to call that c, and this will be the final solution. An alternative form of that would be to express this as ln 1 over cos x plus cos x sine y equals c. This would be ln cos x to the minus 1. And then we can just write that one using log laws. You can write that 1 in front. So it'll be negative ln cos x plus cos x sine y equals c. This is just an alternative form. Of course, you don't have to do that. You can just leave it in. The original form as it was ln sec x plus cos x sine y equals c. This differential equation is different to what we've already done. M is 2y squared plus 3x, n is 2xy. However, the partial of m with respect to y will be 4y, and the partial of n with respect to x will be 2y. And 4y clearly does not equal 2y, therefore the differential equation is not exact. So because this differential equation is not exact, we're going to attempt to make it or turn it into an exact differential equation. And we do that by establishing an integrating factor. And to do that, we need to find an expression in terms of partial derivatives that will give us that integrating factor that we can then use. So those expressions are given as m sub y minus n sub x over n, and n sub x minus m sub y over m. Now, just this notation, m sub y is the partial derivative of m with respect to y, and n sub x is the partial derivative of n with respect to x. So m sub y, the partial derivative of m with respect to y, is going to be 4y minus the partial derivative of n with respect to x will be 2y over n, which is 2xy. So simplifying that, we get 2y over 2xy. 2's will cancel, y will cancel, and this expression equals, simplifies as 1 over x. Now this is an expression that we can integrate quite easily and get the integrating factor. Once you've established one of these expressions and you have a function, an expression that can be easily integrated, there's no need to go and do the same thing for the other expression. We don't have to find n sub x minus n sub y of m, but we'll do it regardless here. So n sub x will be 2y, the partial derivative of n with respect to x, minus the partial derivative of m with respect to y, which is 4y over m, which is 2y squared plus 3x. So simplifying that gives us minus 2y over 2y squared plus 3x, which is not easy to integrate. So we're going to stick with this expression over here. Again, you only have to do either have to work with this expression or that expression. You don't have to work with both to get the integrating factor. Now that we've established an expression for m sub y minus n sub x over n, we're now going to establish the integrating factor. So the integrating factor, in this case, since we've used this particular expression here, is mu of x, and that equals e to the integral of m sub y minus n sub x over n. That's with respect to x. So that is e to the integral of 1 over x dx, which equals e to the ln x, which just equals x. There is another integrating factor if we use the expression, the alternative expression, which is n sub x minus m sub y over m. And if this expression is used, then the integrating factor will be mu of y, and we'll be integrating with respect to y. So that'll be mu of y equals e to the integral of n sub x minus m sub y over m, and that's with respect to y. However, we're going to stick with this expression. The expression we got for n sub x minus m sub y over m wasn't easy to integrate. So we're sticking with the first expression, and all we need to do is work with one or the other. We don't need to work with both of these expressions. We just need one integrating factor. So the integrating factor is x, so we can multiply every term of this differential equation by that integrating factor. So we'll have x times 2y squared plus 3x dx plus x times 2xy dy equals 0. So just cleaning this up, we'll have 2xy squared plus 3x squared dx plus 2x squared y dy equals 0. Okay, we're now going to test to see if this differential equation is now exact. So this expression here, 2xy squared plus 3x squared is the new m, 2x squared y is the new n. So again, we're going to show that the partial derivative of m with respect to y equals the partial derivative of n with respect to x. So m equals 2xy squared plus 3x squared. So the partial derivative of m with respect to y will be 2x is a constant, so we'll just take that out front. The derivative of y squared is 2y. The derivative of 3x squared with respect to y is going to be 0. So the partial derivative of m with respect to y is 4xy. And then the partial derivative, write down n, which is 2x squared y. The partial derivative of n with respect to x will be 2 times y will be the constant. And the derivative of x squared will be 2x, so that equals 4xy. So now the partial derivative of m with respect to y equals the partial derivative of n with respect to x. So therefore the dE is now exact. So the next step is to determine an expression for the function f. So m is the partial of f with respect to x, and that equals 2xy squared plus 3x squared. So we can integrate this expression now with respect to x. So on the left we have the function fxy, Again, we're going to split this up into two separate integrals. So the integral of 2x y squared dx plus the integral of 3x squared dx. And that equals, with respect to x, 2y squared is a constant, so we'll just pull that out in front of the integral sign. 2y squared times the integral of x dx plus, we'll pull the 3 out as a constant, 3 times the integral of x squared dx, and that equals 2y squared times the integral of x will be a half x squared, plus 3 times the integral of x squared is a third x cubed, and we have a constant of integration, which we will call g of y. Since we're integrating with respect to x, we have a function of y only, which will, when we differentiate this expression for f, when we differentiate this expression for f with respect to x, the derivative of the function g of y will be 0. So just cleaning this up, we're going to have x squared y squared plus x cubed plus g of y. We're now going to take the partial derivative of this expression of this function f with respect to y, and then we're going to match it to the expression of the new expression of n that we found, which is 2x squared y. So the partial derivative of f with respect to y, x squared is a constant, so we'll pull that out front. The derivative of y squared will be 2y. The derivative of x cubed with respect to y will be 0. And the derivative of g of y will be g prime y. So that equals, tidying this up, is 2x squared y plus g prime of y. Now, the partial of f with respect to y is n, and that is 2x squared y. Now, comparing the two expressions that we have here for the partial derivative of f with respect to y, 2x squared y appears in both, and clearly g prime of y equals 0. So g prime of y equals 0, and integrating that with respect to y, g of y equals some constant c. So the function f equals x squared y squared plus x cubed plus the constant c, and that equals another constant, we'll call that c1. So really can tidy this all up. You don't need to have two arbitrary constants as part of your solution, so we'll just write this entire expression as x squared y squared plus x cubed equals c. Now just checking the solution, if we find the partial of f with respect to x, we will have 2x times y squared, so we'll have 2x y squared plus 3x squared, and that is this expression here. And if we take the partial derivative of f with respect to y, we will have x squared is constant, so we'll have 2y times x squared, so x squared times 2y. The derivative of x cubed with respect to y is going to be 0, so this just equals 2x squared y, which is the expression that we have there. So the solution is correct.